In a previous video, we talked about uh, how to get velocity, instantaneous velocity, average velocity from graphs of position versus time, how to get values of acceleration from graphs of velocity versus time. In this very short video, we will look at the opposite process. How do we start when we start with a graph of velocity versus time? How do we get a graph of position versus time? Um, uh, and to approach this topic, we're going to start with the simplest of all motions, motion with constant velocity. So here we're given a graph of velocity versus time, and we're going to look at the simplest of all motion, that is motion with constant velocity. So this graph of velocity versus time is a straight horizontal line between time intervals t1 and t2. Well, if we want to find out how far something has traveled during that time interval, t1 to t2, um, with constant velocity, it's very simple. Distance equals rate times time. So we would take the rate, which is the velocity, and multiply by the time interval, the time for which it traveled, delta t. We would take v and multiply by delta t. Now when we take v, this quantity here, and multiply by this quantity here, what in fact are we doing? Well, what we're doing is finding the area under the graph. And so the area under this velocity versus time graph is telling us something about the motion. Not the position, but rather the displacement. How far did something move? Now, if you recall from our previous discussion about the difference between position and displacement, we know that given displacement, we can calculate position, but we also need to know something else. If we want to calculate the final position, but we know the displacement, we also need to know the initial position. And with that, we can calculate the final position. And this is an important point that we're going to have to emphasize, that the area under the graph does not give us position, but rather how far something has traveled or the displacement. The next thing we want to look at is what if the motion that we're looking at is not a motion with constant velocity, but rather more complicated. Say the velocity versus time graph is a curve, something like this, between time intervals t1 and t2. How do we go about calculating um, position or displacement then? Well, we can think of this motion um, as really a whole series of steps uh, of short intervals of constant velocity. In other words, we're going to approximate this curve with a step function that looks something like this, where the object moves at a constant velocity, then a constant velocity, and a constant velocity, and continues. So it's moving through regions of constant velocity, but the constant velocities are changing. Now, this motion would be very similar to the motion that we're looking at, where the velocity is changing gradually and continuously, and it's an approximation to that motion. If we want to find out how far something has traveled, um, what we really need to do is find the area under this curve. Now the area under this curve is rather difficult to find, and that's something that you're going to be working on in your calculus class. But for the time being, what we want to do is understand conceptually what we're doing. To find that area, what we're going to do is take that velocity versus time graph and break it up into uh, small intervals of time, delta t. Here's a small interval, another small interval. Each of these we're going to call the quantity delta t. And what we're going to do is calculate the area of these rectangles. Now when we add up all these rectangles, it'll give us something that approximates the displacement, how far something has traveled during that time interval. Now to get a more accurate value, what we really want to do is find the summation of these areas, but take the limit as delta t approaches 0, as these small intervals here become smaller and smaller and smaller. The limit as delta t approaches 0 of the sum of these rectangular areas gives us an accurate representation of the displacement. Um, in the language of calculus that you'll be learning shortly, uh, we can express this lengthy symbol with an integral sign. That's what the integral really means. It's the summation, the limit as delta t approaches 0 of this summation of v times dt. Well, we change delta t to dt. Again, notation. But this is what we mean by um, uh, this integral representation. It's nothing more than the sum of these rectangles as delta t approaches 0. The important point once again here is you learn how to do the calculus. No question about that you will learn, and it's not very difficult either. But the important point here is that the area under this graph is not the position, but rather it is delta x, the displacement. And we know then that to get the position, to find the position, x2, we need to know the displacement, but we also need to know what its position is at the beginning of the interval. And so from this, we can, given a graph of v versus t, we should be able to then uh, derive the graph of x versus t. Similarly, if we are given a graph of a versus t, here's the graph now of a versus t, the area under the a versus t graph is the change in velocity. The change in velocity from t1 to t2. Now again, this is a change in the velocity, not the velocity, but how the velocity changed during that interval. So in order to figure out what the velocity is at the end of the interval, we need to know the change in velocity, that is the area, and we need to know the velocity at the beginning of this interval. So to go from x to v to a, we know we have to find slopes. To go from a to v to x, we see that we have to calculate areas. But the areas are just giving us the change in a quantity. The area under the acceleration graph gives us a change in velocity. The area under the velocity graph gives us a change in position. From those quantities, we can calculate velocity and position as functions of time. Okay, so that concludes this very short video. Hope it makes sense, and we'll see you later.